Hello students, this is the subject of electronics and electronic device and our topic is semiconductor and its property. Now we can define the semiconductor as it is the material whose conductivity lies between the inductor and conductor. For example, silicon and germanium. Its conductivity can be controlled by adding impurities, which is called the doping, and it's fundamental for creating the semiconductor devices like transistor and ICs that are essential for modern electronics like computer, smartphones and medical equipment. Properties of semiconductor are: the first property we can define as in the variable conductivity, which is low, but it increases with temperature while conductor's conductivity decreases as temperature rises. The second one is doping. By adding impurities in the semiconductor, conductivity can be increased, making it much better conductor. The third one is junction. When two regions with different doping level are combined, they form a junction, which is the basis of for creating electronic equipment. Now, how the semiconductors are used. These are electronic components made with semiconductor materials such as transistor and ICs. Like electronics, they are the foundation of modern electronics, found in everything from smartphones and computers to appli- appliances and automobiles. And its application is ranging from digital logic and memory storage to converting light into signal and vice versa. This is the diagram of semiconductor in which N region and P region are connected with the depletion region. Now, the next topic is bonding forces. In intrinsic silicon, atoms are held together by pure covalent bond, creating a band structure with a valence band and conduction band and band gap. Doping like doping in the silicon metal or semiconductor to create an extrinsic material alter the bonding by introducing impurities. This changes the energy band diagram, creating either N-type or P-type silicon. Now the intrinsic silicon. The energy band of intrinsic silicon is at non-zero temperature. Thermal energy excited the some electron breaking the covalent bond. Charge carrier, the number of electrons and holes are equal, and the bonding in the silicon semiconductor form the pure covalent bond with four neighboring atoms sharing their four valence electron at absolute zero, bonds making the bonds complete, and the material act as an conductor or semiconductor, where we can express in the mathematical form, which is defined as the mass action law, in which Ni square is equals to product of charge carriers of N dot P. Extrinsic silicon we can define as the bonding. This is created by doping with a small amount of impurities, which disrupts the pure covalent bonding structure, and the energy band is N-type, that is donor doping. Impurity atom like phosphorus with 5 valence electron are added. The extra electron is loosely wounded and creates new low energy state just below the conduction band. When these electrons jump into the conduction band, they become the majority carrier. And in the p-type, that is acceptor doping, the impurity atom like boron with 3 valence electron are added. The lack of an electron to complete a bond create a hole. This introduces now the energy state just above the valence band. Allow the electron from valence band to jump into the impurity site with very little energy. Now the charge carriers. the number of electron and hole become unequal in the extrinsic semiconductor. Gap basis. These are the band gap basis. Application of excess energy like light, thermal, electrical, or the addition of extra electron in the system result in the conduction by moving the electron from valence band to conduction band. And in the thermal equilibrium condition, electron can be excited into the conduction band, leaving a hole in the valence band. So the valence band become empty and the whole conduction started in the conduction band. The effective mass of hole, that is mh star, and electron, and for electron m subscript e star, is a quantum mechanical quantity relating the initial resistance to acceleration of each under driving force due to electric field with the periodic structure. We can understand with the help of examples and diagram. Here, the photon with an energy greater than Es can excite electron from valence band to conduction band. And photon breaks in silicon-silicon bond, a free electron and a hole in the silicon-silicon bond is created. Now the simplified band diagram of semiconductor. The first one is intrinsic, second one is n-type, and third one is p-type semiconductor. With the help we can previously defined as the in mass action law, that is n dot p is equals to ni square, where donor and acceptor energy level are shown. These are the diagram of intrinsic silicon and extrinsic silicon. Energy band gap in material. First one is in insulator, the band gap is very much large, and in semiconductor the band gap is uh, larger than the conductor, and in conductor the band gap is very minimum. Carriers in semiconductors, the carriers are electron and holes which carry the current, or with the help of the carrier the current is generated. So electrons are negatively charged carrier, move in the conduction band, while the hole are absence of electron in the valence band, act as positive charge carrier. In intrinsic semiconductor, the carriers must be equal, that is number of electron and holes is equal. But doping with impurity created extrinsic semiconductor where one type of carrier become dominant. This is the definition of electron and hole with their charges as negative and positive respectively. This is the we can understand with the help of diagrammatically of with pure silicon crystal with p doping in n-type and p-type semiconductor. Carrier concentration, extrinsic semiconductor with n-type semiconductor, creating by doping with pentavalent impurity, that is phosphorus, which adds extra electron. Therefore, electron are measured carrier, majority carriers, and holes are minority carrier. And in the p-type semiconductor created by doping with trivalent impurity like boron, which creates a large number of holes. Therefore, holes are majority carrier and electron are minority carrier. And in the intrinsic semiconductor, the carriers, that is electron and holes, are equal. Now the p-n junction. It is an interface or boundary between the two semiconductors, that is p-type and n-type material, namely p-type, n-type, and in the inside the semiconductor. P-n junction is created by the method of doping. P side, that is positive side of semiconductor, has the excess of hole, and the N side, that is negative side of an semiconductor, has excess of electron. Now the unbiased p-n junction, this is the diagram having p-type material having empty holes, and in the n-type material having free electrons, partly separated by the depletion region. Formation, how the p-n junction is formed. As we know, if we use different semiconductor material to make p-n junction, there will be a great boundary that would inhibit the movement of electron from side to other side by scattering the electron and holes. Thus we use the process of doping. We will understand the process of doping with the help of example. Let us consider p-type silicon semiconductor sheet. If we add small amount of pentavalent impurity to this, a part of p-type silicon will get converted to n-type silicon. This sheet will now contain both p-type region and n-type region, and a junction between these two regions formed. The process that follow the after forming the p-n junction are of two types. That is, first one is diffusion and the second one is drift. There is a difference in the concentration of holes and electron, that is carrier, at the two sides of the junction. The holes from the p side diffusion to the n side, and the electron from n side diffuse to the p side. This give rise to the diffusion current across the junction. Now we can start the biasing condition for the p-n junction diode. There are two operating region in the p-n junction diode, that is p-type and n-type, with three biasing. First one is zero bias, having no external voltage is applied to the p-n junction diode. The second one is forward bias, which is defined as the positive terminal of the voltage potential is connected to the p-type, while negative terminal is connected to the n-type. And the third one is reverse bias. The negative terminal of the voltage potential is connected to the p-type and the positive is connected to the n-type. So diagrammatically, we can understand the forward bias of the PN junction as having battery induced in the electric field, built-in electric field, conventional current, and electron current. When the P type is connected to battery of positive terminal and N type to the negative terminal, then the PN junction is said to be forward bias. And when P type is connected to negative terminal and N type is connected to positive terminal, the PN junction is said to be reverse bias. And this is the explanation in which silicon voltage is 0.6 volt, having the resistance in the depletion region become completely negligible. The current flow across is unimpeded. This is the reverse bias of the PN junction. This is the when the P type is connected to battery negative terminal, N type is connected to the positive side, the PN junction is reverse bias. As we understand it in the previous slide, the depletion region become more resistive and thicker if the applied voltage becomes larger. How does current flow in the PN junction diode? The flow of electron from N side towards the P side of the junction take place when there is an increase in the voltage. Similarly, the flow of holes from the P side towards the N side junction take place along with the increase in the voltage. This results in the concentration gradient formation. Charge carrier will flow from higher concentration region to low concentration region. The movement of charge carrier inside the PN junction is reason behind the current flow in the circuit. This is the VI characteristic of PN junction having forward region and reverse region with a breakdown voltage in the reverse region, having zero bias, forward bias and reverse bias. When the PN junction diode is in forward bias condition, P type is connected to positive terminal and N type is connected to negative terminal with the external voltage. And for silicon, the external voltage is 0.7, and in germanium diode, the external voltage is 0.3 volt. The application of PN junction diode is it can be used as photodiode as the diode is sensitive to the light, and it also can be used as solar cell. Third one is the diode is forward bias. It can be used in LED light application, and also it can be used as rectifier in many electric circuits and as a voltage controlled oscillator in varactor. The steady state condition which is also called the equilibrium condition, where the property like carrier density, voltage, and temperature remain constant over the time, even though current may still be flowing. In steady state, the rate at which charge carrier enter and exist in a region is equal, resulting in a constant density. The characteristics of steady states are constant property, transient having have passed, continuous flow, dynamic equilibrium, thermal analysis, and out of equilibrium. Now the breakdown in semiconductor diode, that is two types of breakdown. First one is avalanche breakdown and the second one is Zener breakdown. Avalanche can be defined as uh, it occurs in light doped semiconductor and minority charge carrier gain enough kinetic energy from the high electric field to collide with atom in the depletion region. And in the Zener breakdown, this occurs in heavily doped semiconductor. Very strong electric field is created across the narrow depletion region. And our last topic is metal semiconductor junction. It is a type of electric junction in which metal comes in close contact with semiconductor material. And the oldest type of semiconductor, practical semiconductor device is metal semiconductor. It is the junction either be rectifying or non-rectifying. The rectifying metal semiconductor junction form a Schottky barrier, making a device known as Schottky diode, while the non-rectifying junction is called ohmic contact. Thank you.